Welcome back. This is the second part of section 4.1 on connected spaces, and in which we are going to prove some fundamental properties and theorems about connectedness. First result is the following. If X is a topological space and we have a collection of subsets of X that have a common point, then the union is connected. Try to draw a figure if you like. For example, take a point and consider disks that contain that point. A collection of disks, for example, of that. So the union, as you expect, must be connected, cannot be split. Okay. Now we are going to prove that. So let A lambda be a collection of connected subspaces of a topological space X, and let P be a common point. So the intersection, by assumption, is not empty. So consider a point P in the intersection. We'll prove that the union is connected. So the easy thing to do to prove that a space is connected or a subspace is connected is to reason by contradiction. Okay? Because when we reason by contradiction, we have a separation. So Y has a separation. Y here is the union. So suppose that Y is separated. Okay, so have a separation CD of Y. So what does this mean? It means that Y equal union of C and D. C union D is Y, C intersections D is empty. C and D are both cloped in Y, and they are not empty. Now, since Y is C union D and P belongs to Y, which is the union, therefore P is either in C or in D. Cannot be in both because the intersection is empty. Now, we can relabel them if you like, and you can assume that P is in C, for example. Okay? It's not really a big deal. The C and D, anyway, play the same role. So now we fix an index lambda. Since A lambda is connected by the previous lemma, lemma 4.2, A lambda must be contained in either C or D, but it cannot be contained in D because it meets C, because it contains the point P, which is in C, as you said. Okay, so therefore A lambda is in C. But lambda was arbitrary, so this means that this is true for every lambda. So the union is, which is Y, is contained in C, and this means that D is empty. Right? And that's it. It's very easy. So this is a very simple connectedness argument that illustrates the use of the definition. So this is the first result. Second result is very interesting. If we have a subset A of a topological space which is connected, and B is any set which is contained, which contains A and is contained in the closure of A, then B is connected as well. So in words, if B is obtained from a connected subset A by adjoining some or all its limit points, then B is connected. So in particular, if A is connected, then A bar is connected. But not only that, any set in between is also connected. So imagine, for example, taking a disk, an open disk, and you just add some points on the boundary. Yeah? Not necessarily all the points. For example, take the open disk with an arc or just a point or 2 points. And now the resulting space is still connected. Okay? So if A cannot be split, then B cannot also be split. Okay, rigorous proof by contradiction. Suppose that CD is a separation of B, then by lemma 4.2, so A must be, since A is connected, A must be contained in either C or D, right? So by relabeling the two sets, we can assume that A is contained in C. Okay. Then what do we have? Then by assumption B is contained in A bar, and since A is contained in C, then A bar is contained in C bar, as we know. Okay, so we have this inclusion. But C bar, according to lemma 4.1, actually, C bar intersected with D is empty, okay, because CD is a separation of B. Okay, and therefore B intersected with D is contained in C bar intersected with D. So if the biggest one is empty, then the small one is empty. So B intersected with D is empty. And this is a contradiction because CD is a separation of B. Okay. When I say that CD is a separation of B, it means that C and D are both non-empty disjoint. And actually more is true. The C bar intersected with D is empty and D bar intersected with C is empty. Right, so this is a contradiction. Okay. Third result, the image of a connected space under a continuous map is connected as well. So in words, continuity conserves connectedness exactly as it conserves compactness. So in particular, connectedness is what we call a topological property. So if two spaces are homeomorphic, then they are either both connected or both disconnected or separated. Okay, let us prove that by going back to the definition. So since f is continuous, we can consider f as a map, as a surjective map from x to its image. Okay, we don't care of what happens outside f of x because we want to prove that f of x is connected if capital X is connected. So easiest thing to do, we reason by contradiction. So suppose that f of x is not connected, then it has a separation AB. Okay. Now, so it means that four things, once again, both not empty, both open, they are disjoint, and their union is f of x. So since A is open in the image, the inverse image of A under F is open because F is continuous. And similarly for F minus 1 of D. So therefore, we can write now X as the union of these two sets. So X is, by set theory, is a disjoint union of F minus 1 of A and F minus 1 of B. And this means that X is, so F minus 1 of A, F minus 1 of B would be a separation of X in this case. And this contradicts the connectedness of X. So very simple. Expect such questions in the exam. Okay. Fourth result, also expected. A product of connected spaces is connected. So connectedness is conserved by taking products. Okay, so it's enough to prove that the product of two connected spaces is connected because then we can reason by contradiction on the number of spaces. Of course, here we are taking just finitely many spaces. You will learn about an arbitrary product of spaces next year. Okay, so we'll use the first result. So here's the picture. We have a space X and another space Y that are both connected. We fix a base point AB here in red, and we consider the horizontal slice in green here. This slice X times B. Okay. So this slice, actually, this space is homeomorphic with X, as you may easily check. Okay? Because this is just a copy of X. Okay? This green line is just a copy of the space here. So they are homeomorphic. You should understand that. Just take, you can write actually an explicit. So for example, just take the identity. So the map F from X to X times B would be just X comma B, the identity comma B. And this is clearly a homeomorphism. Okay, now if we consider an arbitrary point X, small x and capital X, and we consider the vertical slice singleton X times Y. Okay. Now this is also connected because for the same reason it's homeomorphic with Y. Okay, and as we said, connectedness is conserved under homeomorphisms. Okay, and according to the first theorem, how can I write? So if you consider now this, the union of these two slices, X times B and X times Y. Okay, and this cross here. it should be intuitively clear that it's connected, but we know that it's connected because this vertical slice is connected and this vertical slice is connected, and they have a common point, which is here, xb. Okay, so this cross-shaped subset of the product is connected, and this is why I called it T sub x. Okay, it's a T shape. And okay, fine. And now, what happens when x varies? Okay, so I have actually, as you may check, or as you may expect, when x varies, Tx cover the product x times y. Imagine that we have these vertical slices varying, so we cover the product. And this is something easy to check. Easy to check that the product x times y is the union of all these T-shaped spaces. And the union is actually connected because it's the union of connected sets having, for example, AB in common. Okay. Therefore, x times y is connected. Okay. So this concludes the fourth result. Fifth result, a little bit more difficult, that when we mentioned in the previous video, the only connected subsets of R are the intervals, including the trivial intervals, which are the singletons and the empty set. So I have to prove, there are two implications to prove here. Let us start with the easy one. So let us prove that if E is a connected subset of R, then it's necessarily an interval. How do I know that it's an interval? What is an interval? An interval of R is just a convex subset of R, which means that if small x and small y belong to E, then all the points between x and y are also in E. Okay, this is the definition of an interval. And then you know that we have 11 kinds of intervals, 2 of them being trivial, the empty set and the singleton. And then we have AB open, closed, semi-open, and of course the unbounded A infinity, minus infinity A, and so on. So we have 11 kinds of intervals. We can prove that. So suppose that E is connected, but it's not an interval. So we have to negate the condition of being an interval. So when you negate that, you'll find 2 points x and y in E, but the interval or the straight line segment joining x to y is not totally contained in E. So there exists a point between x and y which is not in E. This is the negation of saying that E is not an interval. But then we have a separation of E, because you can write E as the disjoint union of 2 open sets. E intersect the open interval minus infinity z. This is open in E. And of course, it's not empty because it contains x. And the second one, E intersected with z plus infinity. It's also open and not empty because it contains y. So then we have a separation of E. And this contradicts the connectedness of E. Okay, so this is easy. Okay, now conversely, suppose that E is an interval, and you have to prove that it's connected. Okay? Now, it should be intuitively clear why it's connected, because it's one piece. But how to prove that by going back to the definition? We do the normal thing. We reason by contradiction, because it's easier to work with a separation. So suppose that E has a separation, AB. So A and B are 2 subsets of E that satisfy the 4 properties, being non-empty, disjoint, cover E, and open. Okay, since A and B are not empty, so we choose an element small a in capital A and an element small b in capital B. And we may assume that small a is less than b. Otherwise, we relabel capital A and capital B. Okay, now, since capital B is an interval, by definition of an interval, the straight line segment joining A to B is contained in E. Okay, so all the elements between A and B are belong to E. This is the definition of an interval. Okay, and now we can write the closed interval AB as a disjoint union of 2 sets. Okay? The first one we call it A0. The second one we call it B0. Okay? So we can write the closed interval small ab is the disjoint union of capital A0 union capital B0. Okay, now since A0 is not empty and it's bounded from above by B, it has a supremum. Okay, so let's see B the supremum. Okay, now we'll reach a contradiction, but we have to distinguish between two cases. First case, C, the supremum of A0 belongs to A0. Okay? What happens in this case? Then necessarily C cannot be equal to B, because C is equal to B, so B by definition would belong to A0 and B0. Okay? But the intersection is empty, okay? Because A and B are disjoint. So what does it mean that C is not equal, is different from B? It means that either C equal A or C is strictly between A and B. Okay? Because remember that capital A0 is contained in the closed interval AB, but an element in, so C cannot be B, so it's bigger or equal than A and strictly less than B. So in both cases, because capital A0 is open in the closed interval AB, we can find an interval of the form C plus epsilon, totally contained in A0. Okay? Actually, if C is strictly bigger than A, you can take C minus epsilon, C plus epsilon. But if C equal to A, you can just take A plus epsilon. Okay? Doesn't matter. Okay, so in particular, so this whole interval is contained in A0. So in particular, take a point between C and C plus epsilon. This point belongs to capital A0. Okay, but if Z is in capital A0 and C is the supremum of A0, then C is less or equal than the supremum. So it's less or equal than C, but this is a contradiction because Z is strictly bigger than C. Okay, so in this case, we have a contradiction. Now, the other case is that C is in capital B0. And in this case, it's a little bit symmetric. So C cannot be equal to A because A belongs to both A0 and B0. So this is impossible, actually. So for the same reason. So either C equal B or C is strictly between A and B. And in either case, we can find a positive number epsilon such that the interval, semi-open interval, C minus epsilon C is contained in B0. If C is strictly than B, we can take C minus epsilon C plus epsilon. So now what do we have? Since C is the supremum of A0, by a property of the supremum, C minus epsilon is not an upper bound. So we can find an element in C minus epsilon C which is contained in A0. And what do we have now? We have a contradiction. Okay, so and therefore in both cases we have a contradiction because A0 and B0 are disjoint. Okay, so this concludes the proof of the fifth result, and I will end with a theorem that you encountered in first year. It's called the intermediate value theorem, but it's a general version of what you learned because instead of considering a function from an interval of R into R, we can consider a function from an arbitrary connected space into R. Okay, so if X is a connected topological space and F is a continuous map from X into R, and if we take 2 points A and B in X, so their images under F are real numbers. So F of A and F of B are real numbers. If R is a number between F of A and F of B, so either F of A less than R less than F of B, or F of B less than R less than F of A, then there exists a point C in the space whose image under F is precisely this this intermediate value R. And this is just an easy consequence of two previous results, combining these two. First result is that connectedness is conserved under continuous maps. So the image of capital X is connected. But by the previous result, a connected subset of R is necessarily an interval. Okay, so for example, suppose that F of A is less than F of B, and consider an element R in between. Okay, so since F of X is an interval, then by definition of an interval, the straight line segment F of A, F of B is contained in F of X. So therefore, in particular, R, which is here, is in F of X. What does it mean that R is in the image? It means precisely that R is equal to F of C for some C. And that's it. So this concludes section 4.1 and this video. So thank you for your attention and see you next time.